So for this video, we're going to focus on graphing rational functions. So first, before we get to actually graphing, we're going to talk real quickly about how do we find vertical asymptotes, how do we find horizontal asymptotes, and then we'll get into a couple examples on actually graphing rational functions. So first off, just keep in mind that a rational function is a function that's set up as a fraction, right? So you're going to have a fraction where you have a polynomial in your numerator and a polynomial in your denominator. And again, keep in mind that a polynomial is just some set of terms, right? Where you have a coefficient, a variable, that type of thing. So maybe take a look at example C. Our numerator here is a trinomial, right? We have 1, 2, 3 terms there. All right, so a polynomial could be one term. It could be a million terms, really. So it's just a bigger grouping in fraction form like that. So our typical steps in graphing rational functions are as follows here. So number one is to determine symmetry. Does it have y-axis symmetry? Does it have origin symmetry? Now, I'll be honest, sometimes I'll do this step, sometimes I'll skip it and go straight into finding my, my specifics, my actual points and things like that. So I'll work an example where I do this step and one where I don't. But otherwise, I like to kind of just jump straight into the problem and start finding concrete points, right? Let's find the x and y intercepts. Let's see what vertical, horizontal asymptotes we have. And let's just plug in maybe, and let's find some additional points, right? By plugging directly into the function, getting some points, to wrap up our graph here. So for the most part, these are going to be sketches with some specifics. So it's not going to be exact, but it's going to be pretty darn close to what your graph would look like here. So before we get into working an actual example here, let's find the vertical asymptotes of the following examples. So a vertical asymptote, I always kind of just think of it as an imaginary line on my graph. I typically draw it, well, first off, backing up just a second, a vertical asymptote, I always think of it like as an imaginary, a dashed line on my graph. It's a vertical line straight up and down, just like this. So for your vertical asymptote, essentially in order to graph it, you're going to go left or right on your x-axis. All right, we'll talk a little bit more about that. And then we're just going to graph a vertical line. Now, for the most part, your graphs, when it comes to asymptotes, they like to be near your vertical asymptote or your horizontal asymptote. They like to be near it, but they don't necessarily always cross or, go across this here. So, for example, your graph will like to be drawn towards it, and then it's just going to hug it and follow it, and it's going to just run parallel to it forever and ever for the most part here. So do something like that. Now, every once in a while, we do have examples that don't follow the norm, which is why I always say, for the most part, this is what it'll do. There are some examples where you would cross asymptotes, but for the most part, your most common cases are going to be something like this. I kind of think of them as magnets. Your graph wants to be near it, but it's always just going to hug it and be next to it right over there. In order to find your vertical asymptote, what we're going to do is we're going to set our denominator equal to 0 and solve. So if you see right over here, this is our step. So P of x is going to be our numerator, Q of x is going to be our denominator. So to find any vertical asymptotes, set that denominator equal to 0 and solve. So let's do that with these examples here. Example A, our denominator is x squared minus 9. And the step says set that equal to 0 and solve. Now, in order to solve this is a quadratic equation. I am solving this using the square root property. I am going to add that 9 to the other side, which is going to let me drop down x squared is going to equal to that 9. Get rid of that square by taking the square root of each side. On the left-hand side, square root and square cancel, so we can drop down that x. And on the right-hand side, the square root of 9 is a plus or minus 3. So we have two vertical asymptotes here, one at a positive 3, one at a negative 3. So maybe we could pretend this is our positive 3. In this example, that would just mean that we would also have one over here at a negative 3. Moving on to the next example, again, set your denominator equal to 0 and solve. So here our denominator is x squared plus 9. And we're going to set that equal to 0 and solve here. So I'm going to start by subtracting 9 on each side. That's going to give me x squared on the left and negative 9 on the right. Take the square root of each side. And on the left-hand side, square root and square cancels to give you x. On the right-hand side, taking the square root of a negative number leaves you with imaginary numbers. And when it comes to doing sketches here, we don't want the imaginary world. So we only want actual concrete solutions here. So because our solution would give us something that's imaginary, right? Taking the square root of a negative, we can't actually have that. This would technically be 3 plus or minus 3i. But again, we're not graphing in the imaginary world right now. So because our only solutions are imaginary, that actually means there are no vertical asymptotes here for this example. Moving on to example C. Again, we want to take our denominator, set it equal to 0, and solve. So when I set this equal to 0 and solve it, it's going to be slightly different than my other ones here because this denominator here is in factored form. Now, if it's in factored form and I want to solve it, we're just going to use the zero factor property that says split each factor up, right? We have x, x minus 2, and x plus 5. Split them each up. Set them each equal to 0 and solve. Well, the first one gives us x equals 0. The second one here, well, add that 2 to the other side, and x equals a positive 2. And then over here, subtract that 5 on each side, and x is equal to a negative 5. So for this example, we would have 3 vertical asymptotes, right? At 0, 2, and a negative 5. And our next grouping of examples, we are going to work on finding horizontal asymptotes. Now, in order to find horizontal asymptotes, what we're going to do here, this is kind of, I kind of call it a comparing game. What we're going to do is we're going to compare the numerator to the denominator, specifically the degree of the numerator to the degree of the denominator. So if we look at our numerator, for example, d, right? So our variable here, x, has a power of a 1, right? And since that's our only variable, the degree of our numerator is a 1. For our denominator, here's where our variable is. There's only 1, right? You always want to find your highest power. But here, since we only have one x, and it's to the second power, right, our degree for the denominator would be a 2. Right, so we're comparing a 1 in our numerator to 2 in our denominator, right, or depending whatever the problem says. Right, but what we want to look at in order to figure out the horizontal asymptote, it says if the degree of the numerator is less than the denominator here, right, so n represents the degree of our numerator, m represents the degree of our denominator. So if the numerator degree is less than the denominator degree, your horizontal asymptote is going to be y equals 0. If they're equal to each other, right, if they're both the same, the top is a 3, the bottom is a 3, then your horizontal asymptote is equal to this a sub n over b sub n, right? It represents the coefficient of those terms. So like maybe, well, you know what? I'm going to talk about that a little bit more when we get to the problem that involves that. And the third one says when the numerator degree is greater than the denominator, there is no horizontal asymptote. So let's go ahead and just talk about this here. So with D, we said the degree of the numerator is a 1, the degree of the denominator is a 2, right? So the numerator is less than the denominator. That means that this is going to be our first example here where n is less than m. And according to the rules, if the numerator degree is less than the denominator degree, your horizontal asymptote is y equals 0. That's what it's going to be. Okay, let's take a look at example E. If we look at our numerator, that degree is a 2. If we look at our denominator, that degree is a 2. Those are the same. If they are the same, that's where n is equal to m. And it says if they are the same, you want to look at the coefficients, so the numbers in front. That means I'm looking at a 4 here and then a 2 here. So I want to look at the fraction 4 over 2. Now simplify this, because when we simplify this, this is our horizontal asymptote. 4 over 2 simplifies to a 2, right? Just divide it out. So that means our horizontal asymptote, it needs to be written y is equal to whatever that is. So y is equal to a 2, right? That's what we got here. So y equals 2 is our horizontal asymptote. It's just going to look like a horizontal line on our graph. Example F. If we take a look at example F, in our numerator, we have a degree of a 3. And our denominator, we have a degree of a 2. So that means our numerator is greater than our denominator, right? 3 is bigger than a 2. So that means we're looking at this one where n is greater than m. And it says if that happens, there is no horizontal asymptote for that example here. So let's graph the following example here. So we're going to graph, let's see, f of x is equal to 2x minus 1 over x minus 1. Now we say, if worse comes to worse, and maybe you're taking a test or something like that, and you get stuck when it comes to graphs, I always say, maybe make an XY table and plug in values. So what you could always do, if I take a look at my graph, if I get completely lost and I get blank, right? I just can't think of, what were those rules to find the horizontal asymptotes and vertical asymptotes. Maybe I forgot how to find the x and y intercepts. I would just say start plugging in numbers here. Start plugging in values on your x-axis. Plug in a -3 for x. Plug in a -2. Plug in a -1, a 0, a 1, a 2. Right? Plug in something for x. Plug that into your equation. Simplify it. Get a value. Get something for y. That'll give you a point on your graph. Plug in a different number. Simplify it. Plug in another one. And this will give you point after point after point that you can just plot on your graph, connect the dots, and call it a day. But, let's actually try and graph this by the techniques, laid out here. Right? In order to graph, we're going to find symmetry, the x and y intercepts, vertical, horizontal asymptotes, and then if we need to, plug in and find additional points. Now, for this particular example, I'm not going to find the symmetry for it. This one does not have symmetry, but I'm going to skip that step for right now. I'll show you that step in the next example. So I'm going to start with finding the x and y intercepts here. So I'm actually going to start with the x-intercept. And in order to find the x-intercept for any function, you want to set the function equal to 0 and solve. But since we're dealing with a rational function, we can actually save ourselves a step here. In finding the x-intercept, set the numerator equal to 0 and solve, right? So set your numerator equal to 0 and solve. That means for our example, our numerator is a 2x minus 1. Set that equal to 0 and solve. Add the 1 to the other side to get 2x is equal to 1. And divide 2 on each side to get x is 1/2. So that means we have one x-intercept. It's going to be right over here at a positive 1/2. I'm going to go ahead and plot that. Let's find our y-intercept. And let's see, going back to our steps here to find our y-intercept of a rational function, we're going to find f of 0. That means we're going to plug in 0 to our function. Right? If we're going to find f of 0, we're going to take our function, and we're going to plug in 0 for every single x, right? Instead of x, replace it with a 0. And simplify this. When we simplify this, 2 times 0 is 0, so that's going to leave us with a -1 up top. And 0 minus 1 is a -1. And if we simplify -1 over -1, that is just a positive 1. So our y-intercept is going to be right over here at a positive 1. Okay. Next thing, let's go ahead and find any vertical asymptotes. We're going to find our vertical asymptotes by taking our denominator and setting it equal to 0 and solve. So our denominator is x minus 1. So we're going to set that equal to 0 and solve by adding 1 on each side. And x is equal to 1 as our vertical asymptote. So that's not a point. Keep in mind that as an equation of our line here. So what that tells us that here at a positive 1 on our graph, we have a vertical asymptote. So an imaginary line here at a 1. So I'm going to go ahead and plot that. Let's now find our horizontal asymptote. So a horizontal asymptote is a matter of comparing the degree of your function here. So in our numerator, our degree is a 1. Again, remember, if there's not an exponent there, it's understood to be a 1. The degree of our denominator is also a 1. So that means the degrees match. And if the degrees match, according to the rules, if they are equal to each other, you're going to look at the coefficients in front. So going back here, look at the numbers in front of those x's. We have a 2 here in the numerator over a 1 in the denominator. Same thing, if there's not a number in front, it's understood to be a 1. So for our horizontal asymptote, we had a 2 as our coefficient in the numerator, 1 is our coefficient in the denominator, which simplifies just to a positive 2. So we have a horizontal asymptote here at positive 2. We've gone through our x and our y intercepts. We've gone through our vertical and horizontal asymptotes, and this is the graph that we're currently looking at here. Now, if we kind of just do, I would maybe say just pause maybe the video real quick and maybe just go to Google and type in graphing or graphs of rational functions, right? And go over to the images and just take a look real quick at the images so that you can get an idea of what some of these examples look like here. Because for the most part, you'll have a lot of these that tend to follow very, very similar shapes and things like that. Because we don't have a lot plotted on here, but for the most part, there are some just knowns of these graphs that we can kind of assume at this point. So I see that I have 2 points here in this bottom left section, right? I have a vertical asymptote, a horizontal asymptote that are kind of splitting this into 1, 2, 3, 4 sections here. So I have points here in the bottom left. And kind of just rules of rational functions. So you tend to have points in opposite sections here. So since I have points in the bottom left, I more than likely also have points in the top right, and these two will be blank. Or, if I had points in the top left, then I would probably also have points over here and not in these two sections. Now, that's not always, but for a lot of the times, it does tend to follow that process right over there. But in this bottom left section, I do have these 2 points, and I can say that these 2 points are definitely going to connect, right? But I can also use what I know about asymptotes in the fact that my graph wants to be near them. And if I connect these 2 dots, right, going after this point here, my graph is going to want to be near this asymptote, and it's going to want to just run parallel to it, getting closer and closer and closer without touching it, without crossing it. Same thing up here. Once we connect these 2 dots, our graph is going to want to be near, and it's just going to run, and it's going to follow this graph. So for the most part, those are your behaviors of asymptotes and these types of graphs. Now, what I'm going to do is I'm assuming that I also have points in the top right section over here. But when it comes to math, you never just want to assume. You need to prove it. All right, so what I'm going to do is I'm going to pick the points 2 and 3. All right, because I'm going to pick any points over here to the right of this line. This is a 1. All right, so I'm going to pick 2 and 3, the next 2 numbers here. Don't go too big. All right, we don't necessarily always want to know what's going on over here. We want to keep it close and seeing what's happening over here. So I'm going to pick when x is equal to 2 and when x is equal to 3. So essentially, I'm going to plug into this chart here. I'm picking 2 and 3. So when x is equal to 2, all right, I'm going to plug in 2 into my function here. So it's going to be 2 times 2 minus 1. Over, what did that say? 2 minus a 1, right? So we're just plugging in a 2 for our x and simplifying. In the numerator, 2 times 2 is a 4, and 4 minus 1 is a 3. And our denominator, 2 minus 1, well, that's a 1, giving us 3 over 1, which is a 3. That means when x equals 2, y equals 3. That gives us the point 2, 3, which means if I go right 2, up 3, I know I have that point right over there. Let's also plug in 3. All right, so if I plug in 3 into my equation and simplify, let's see what we get. 2 times 3 is a 6. 6 minus 1 is a 5. And the denominator, 3 minus 1 is a 2, which gives us 5 halves, which when we simplify that, that is a 2.5. So when we plug in 3 for x, we get 2.5 for y. So if I go over 3 and then up, 2.5, that's about right here. Go ahead and connect these dots. And then again, on either side of that, over here on the left, our graph wants to be near our asymptote, and it's going to curve, and it's going to follow that. Over here on the right-hand side, same thing. It's just going to want to be near that asymptote and forever continuing to follow that. And this is what our graph would look like. Now let's graph another example here. Now with this example, I am going to go through all the steps, starting with determining the symmetry here. So we want to determine, is it an even or an odd function? If it's an even function, it has y-axis symmetry. That means we can plug in a negative x for x. So let me kind of give you a hint here. If every single x variable on your function is raised to an even number, which we have here, right? We only have 2 x's in our problem, and they're both raised to a power of 2. If that's the case, it is going to be an even function, right? Every variable is raised to an even power. This is an even function. Now, we can definitely do the step here, right? So in order to determine the symmetry here, you're going to plug in. The rule says to test a y-axis symmetry, which is an even function, plug in negative x for x. Do they equal each other, right? Does f of x equal what you would get if you plugged in negative x for x, right? So this is our f of x. So plug in negative x to your function, right? Instead of x here, plug in a negative x. And then in the denominator, same thing, negative x squared minus 4. Now this is f of negative x. Simplify it. Will it equal your original function? Now when I simplify this, here we have negative x squared. Well, negative x times negative x is x squared. And we have that 3 in front. Same thing in our denominator. Negative x times negative x is x squared minus 4. So we do get the same thing as our original function. This is an even function, which means if we take this y-axis and we fold it, right? So pretend the left side and the right side. If we were to fold this up like this, every point on the left is going to match up with every point on the right-hand side. Now, the origin symmetry does not work here. So it says, does f of x equal the opposite of the function here, right? So this is what our f of negative x is here. In order to determine origin, you would find the opposite of the function, which means I would be taking the opposite of the whole function here. So it's a negative to the front. Right? This would be negative 3x squared, which is not the same thing as our f of negative x here, our original, right? So this does not equal this. So this one only has y-axis symmetry. So what that would tell me is if I knew that a point was over here on this side, I know that I could also mirror it on this side over here. Everything on the left matches up with everything on the right. Now let's get straight into our actual points here. So finding the x-intercept. Keep in mind the step for finding the x-intercept says to take the numerator, set it equal to 0, and solve. We are going to get a 0 here because we're going to divide by 3, which is going to give us x squared is equal to 0. Remember, 0 divided by anything is 0. To get rid of that squared, we need to take the square root, and x is equal to 0. So that means our x-intercept, which is also a y-intercept, is this point here. So we can see here when we find the y-intercept, we should just get 0. Keep in mind that finding the y-intercept, you are plugging in 0 into your function and simplifying, but we get a 0 in the numerator over a negative 4, which is still a 0. So this point here represents our x-intercepts and our y-intercept there. Now, let's find vertical asymptotes. In order to find vertical asymptotes, you're taking your denominator, setting it equal to 0, and solving, which means we are going to add a 4 to the other side to get x squared is equal to 4. Get rid of your square by taking the square root of each side. That's going to give us x on the left, and the square root of 4 is a plus or minus 2. So that means we have a vertical asymptote here at a positive 2, but we also have a vertical asymptote here at a negative 2. Let's find our horizontal asymptote, which means we need to compare. Compare the degree of your numerator. The degree of our numerator is a 2. The degree of our denominator is also a 2. And again, going back and remembering the rule, it says if the degrees are equal to each other, you want to use the coefficients in front, which means for us, the numbers in front here, 3 in the numerator over a 1 in the denominator, right? We have a 3 over 1 here, which is just a 3. So we have a horizontal asymptote at a positive 3. So, right, we went through and we determined the symmetry, right? And we saw that this had y-axis symmetry. We found our x and y intercepts. We found our vertical horizontal asymptotes. And this is what we're looking at, which doesn't give us a whole bunch of points for our graph. Our last step says plot additional points here. So when I'm taking a look at this section, so earlier when I mentioned, so general rules of rational functions is you typically have points in opposite sections or catty corners. So if I have points in the bottom middle section, right, notice we have 6 sections, top left, top middle, top right, bottom left, bottom middle, bottom right. If I have points here in the bottom middle, That means more than likely I have points in the top left and the top right. Those are kind of just general, right, unknown, unspoken rules of rational functions here. Right, so that's what I'm going to assume. But again, we're going to do that last step, plot additional points in order to figure out. Also, looking here at the middle section where I do have one known point, it would make more sense that I'm going to have a graph that's going down instead of up, because if this graph goes up on either side, notice that it's going to be blocked in by all of these asymptotes. So it does make more sense that we're going to go down here. So I'm going to start with that. I'm just going to take a positive 1 here, and I'm going to plug that in. All right, so I'm going to make an XY table. And the first point I'm going to plug in is a positive 1. Do keep in mind that with our symmetry, whatever point I find on this right side, I can mirror it here on the left side. So let's see, I'm going to plug in for x is equal to 1. So that means take our equation here, which is 3x squared over, well, x squared minus 4. So x squared minus 4. Simplify this. We're going to get a 3 up top and a negative 3 down bottom, leaving us with a negative 1. So when x equals a positive 1, y equals a negative 1. That gives me the point 1, negative 1. And if I have the point over here, if I go over 1, down 1 here, I should be able to go over 1, down 1 here. Again, mirror it on each side. So it looks like here I have a negative parabola here. So if I connect the dots here on the left, and again, it's going to want to hug that asymptote to look like this. Same thing on the right, connect those dots and go towards your asymptote. And it looks like we have a parabola here in our middle section. Now let's go ahead and find points here. So again, I'm going to plug in points over here and just mirror it on this side using our symmetry. So the next point I'm going to plug in is a 3. All right, so let's see, plugging a 3 in. So let's see, that's going to give me a, let's see, so plugging in a 3 for x, all right, is going to give me this here. So let's simplify. Let's see, 3 squared is 9, and 9 times 3 is 27. Over 3 squared is 9, and 9 minus 4 is a 5. 27 divided by 5 is a 5.4 there when we simplify that. So it looks like we have 3 and 5.4, which means we will also have the point negative 3 and 5.4. Right? So go to the right 3, and then let's see, 1, 2, 3, 4. 5.4 is going to be somewhere around here. And then to the left, 1, 2, 3, and 1, 2, well, negative 5.4 should be somewhere around there. All right. Now, I feel better just finding at least one other point here. So I can assume here when we connect the dots, it's going to go up on this side here. So let's just see what's happening on this side. So more than likely, this is going to continue to curve down like this. But let's go ahead and prove that. So I'm going to go ahead and just plug in for 5 and just see what happens when we plug in a 5. When we plug in a 5, 5 times 5 is 25, and 25 times 3 is a 75. In the denominator, 5 squared is a 25, and 25 minus 4 is a 21. When we divide that, that is about a 3.57, so about a 3.6. So let's see, when we plug in a 5, we get about a 3.6. So that's going to look like over 5, up a 3.6, somewhere around here. Which means same thing over here. I'm going to have a negative 5 and then about a 3.6 there. So it does look like it's curving and doing what I thought here. It's going to connect with that point and it's going to hug that asymptote. Same thing on this side here. So this is what our graph would look like.